Hello, my name is Zishan and welcome to Easy Math. Today we're going to look into PMI, that is proofs by mathematical induction from IBHLAA. Well, in IBHLAA PMI, this particular topic, there are five kinds of questions that can be asked, out of which we are going to do divisibility today, which is proving that one particular expression is always divisible by a number. And of course, there are more of them. There is inequality, there is sum to n terms, and all of this. We will go one after the other. This is how we will cover this whole chapter. Today, we're going to look into some divisibility questions. So, here is one. Prove that this is divisible by 3 for all n belonging to z plus. So, that's z plus is supposed to be the set of positive integers, starts with a 1. Okay, so let's go. Let's see. And see, although I'm going to go tell you about it um, in short as of now, but I'll show you the proper structure of it. First, let's go show that this is always divisible by 3. We go, uh, first things first, we go start with the base case. Now, what is base case supposed to be? Well, that's where you check if the expression here is divisible by 3 for the smallest value of n. In this case, if n belongs to positive integers, set of positive integers, the smallest value it can be is a 1. So we're going to check for n equal to 1. So 1 cube plus 11 into 1 is what n cube plus 11n is going to be. And it comes out to be a 12, and it is divisible by 3. There, done. So proving that this is divisible by 3 when n is a 1 is the first step we do. Second step, it's known as the inductive hypothesis. This is where we assume that the expression is divisible by 3 for n equal to k. So we're like, let's assume n cube plus 11n is divisible by 3 for n equal to k, or a proper statement we write k cube plus 11k is 3 times some integer m. So that is our assumption. That is known as the inductive hypothesis step. And then we do proper induction. So final step, that's your proof. That's your proof. You call it induction. That's where I'm like, now we have to prove that it's divisible by 3 for n equal to k plus 1, or k plus 1 cube plus 11 times k plus 1 is 3 times some integer again. That is what we want to prove. Okay. Now the step that we have done here is going to be used in this proof here, in the third step. Okay, let's see how. So we go expand what we have, k cube plus 3k square plus a 3k plus a 1 is what this part of it expands to, plus a 11k plus a 11. Where has this come from? Well, that comes from the fact that, I'm going to write it somewhere else, the fact that a plus b whole cube, is supposed to be a cube plus 3a square b plus a 3ab square plus a b cube. That is where k plus 1 cube comes out to be this here. Okay, so that is a formula you would want to write. It's a very important formula. So we go from here. Now I'm going to try to bring what I have here in here. How? Well, by rearrangement. So I go k cube plus 11k plus. So I'm going to bring these two together, and you have a 3k square plus a 3k plus a 12. Now what I see is this I've already assumed to be 3 times m, and this is 3 times k square plus a k plus a 4. What you're looking at is a 3 times m plus this whole thing, k square plus k plus a 4, which can actually be written as 3 times p. It's going to be an integer. So the point is, that is the end of your solution. You have proved that this thing comes out to be equal to 3 times some integer, and there it is. That's your solution. But that it needs to be better structured. Okay, wait a second. So a better structure of it, a structure which fetches you all the 7 marks. I'll show it to you. You watch it carefully. I've divided it into sections. There it is. There is your section number 1, section number 2, 3, 4, and 5. It should have you checking it for the base case. It should have a proper statement where you assume that it's equal to n equal to k, and it is a factor of 3. Uh, that is how your inductive hypothesis comes about. This is your IH step. And then there is the proof part, which I showed just now there. If you can see, there it is. Me coming to a 3p is the part that I did, and that was the third step. But what are the fourth and the fifth step? Fourth and the fifth step is where you conclude your entire PMI thing. You're like, oh, so nq plus 11n is divisible by 3 when n is equal to a 1. And I assuming that it is true for n equal to k, it also comes out to be true for n equal to k plus 1, then it should be true for all n belonging to z plus. That's your fifth and final statement, and that is how you fetch all the marks there are. There are 1 or 2 marks for this step, 1 mark for this step, 2 or 3 marks for this step. So that's about 2 marks here, 2 marks here. It's about 7 marks. This is how these are going to be distributed. Remember, each step is important. If you miss out on any one of them, you're going to lose marks. Okay. I'll show you another question, which is about divisibility again. So this is divisible by uh, 576. You want to prove that this is divisible by 576. And again, base case, we're going to go n equal to 1. So that's a 5 to the power of uh, 2 minus 24 into 1 minus a 1. That is your base case. Comes out to be 25 minus 24 minus 1. That's a 0. And yes, 0 is divisible by 6. So it is true for n equal to 1. Now we go do the inductive hypothesis where like we are going to assume. So again, what is the statement like? Let's assume 5 to the power of 2n minus 24n minus a 1 is divisible by 576 when n equal to k. So you go, this implies that 5 to the power of 2k minus a 24k minus a 1 is 576 times some integer m. Okay. So you go, now set up the proof. Proof is where you're like to prove that it's true for n equal to k plus 1, meaning 5 to the power of 2 times k plus 1 minus 24 times k plus 1 minus 1 is 576 times some integer there. This is what I want to prove. Okay, so let's go. I go expand this. This becomes a 5 to the power of 2k plus a 2 minus 24k minus 24 minus a 1 equals, um, I'm going to go do the left hand side. Okay, that's how you go. This is what you want to prove. I'm going to try to bring this in here on the left side. Okay, so let's go left hand side. So this is a 5 to the power of 2k multiplied by 5 to the power of 2 minus 24k minus 25 is a 0. And I can go do a 25 into 5 to the power of 2k minus 24k minus 25 equals 0. Now the point is I'm going to have to bring this in here. Okay, so how do I go about it? Well, I can write this thing as 25 into 5 to the power of 2k minus 25 into 24k plus 24 into 24k minus a 25 equal to 0. And I can also bring a 1. Let's bring a 1 here. Minus a 1 minus a 24 minus a 24 equals 0. Look at what I did here, okay? Watch. Let's bring this thing here. A highlighter. I split this into that and and this into that. Okay, I don't think that's gonna work though. Wait, give me a second. I'll correct it quickly. I say that minus 25 can actually be written as, uh, well, I don't think I need to split this. Hold on, give me a second there. And we have a, a 25 here. See, you have a minus 25. We're going to keep that negative 25. And you watch how this comes about. Why am I equating it to a zero though? No need to put up a zero here. Okay, so there, negative 25 as it is. Only this negative 24 splits into these two, and you'll see why I'm doing it in a bit. So from this term now, this term, this term, and that, I'm going to take a 25 out common. What I get is a 5 to the power of 2k minus a 24k minus a 1 plus, so this, and this with a 25 out common remains with that in the bracket. And then you have 24 in a 24 multiplied. That's literally a 576k. And now comes the inductive step where I've already assumed that this is a 576m and a factor of, and a multiple of 576. So there it is, 576k again. And now you know you can take a 576 out common, and a 25 plus 1 is what you, 25m plus a 1 is what you remain with. And yes, 576 multiplied by some number, some integer is this expression, this expression. So you have come to a 576, 576p right there. Done. And that again is the way to do it. The only trick here was to bring your inductive hypotheses into your proof. What I did is I split this thing into these two for me to be able to take a 25 out common from first, second, and the last term, so that you remain with a 576m from the inductive hypotheses in your proof. And now the whole thing is a multiple of 576. That's your proof. I'll show you another way of approaching the same question. This time, again, same structure: step one, step two, step three, step four, and the final conclusion out there. Okay, that's how these numbers are going to be distributed. That's me checking for the base case. That's me assuming it to be 576m when n is a k. And then this is what I want to prove. Uh, it's equal to 576 times p. And then I go do the LHS part, where this time what I did is I took in the expansion for n equal to k plus 1, I took a 25 out common from here, from these two, this one and this one. Well, I split the 25 and, yeah, 24. Okay, I take a 25 out common. Now, this is where you are. Well, this is what it'll be. 5 to the power of 2k minus 1 is going to be 576m plus a 24k. That comes from your inductive step. 576, 5 to the power of 2k minus a 1 is 576 plus a 24k. So I replace it with that. And now when I expand, I come to a very nice 25 into 576m plus a 576k. And again, the whole thing is a multiple of 576. So again, same stuff. Okay, so that was divisibility. Now you can go, or I am gonna have to show you the marking scheme, the official marking scheme for these. So let's go how to go about it according to the marking scheme. So n equal to 1, that's your base case. There. This is your base case. This is your inductive hypothesis. And this is your proof. And then they are like, if it's true for n equal to 1, and if n equal to k is assumed to be true, this implies that little sign there, this sign there, this sign there is read as this implies that. There. Hmm. This implies that it is true for n equal to k plus 1, then it is true for all. Hence, it is true for all n belonging to z plus. So, how do you conclude? You write this. These words should be seen in your final statement, the conclusion. If it's true for n equal to 1, and if n equal to k is assumed to be true for this, it implies that it comes out to be true for n equal to k plus 1. Hence, it should be true for all n belonging to z plus. So, there are marks for these statements. Okay. So now, what your job should be is to practice more of these. I'll show you the questions you want to do. Wait a second. So this is the question you want to do. This one question, take a screenshot of this. This is one you want to do. And I'll show you another set you would want to do. I'll let you take a screenshot. First, take the screenshot for this one. I'll wait. And then you want to do these. This one, fourth, fifth, sixth, seventh. Seventh is a very nice question. Seventh one, eighth. These 4 to 8 is something that you would want to do. Of course, 1, 2, 3 are also nice, but these are nice. Remember, for a term to be divisible by 6, remember, if there is n into n plus 1, two consecutive integers or k into k plus 1 in your proof, it means that these are two consecutive integers, one of them being odd makes the other one even. If it's a 2k times 2k plus 1, you know that 2k is even and 2k plus 1 is odd. And even an odd number multiplied will always be even. And 3 multiplied by that pair, 2k and a 2k plus 1, will always be divisible by 6. 3 multiplied by any even number is always divisible by 6. It's also always a multiple of 6. That's one thing when you want to remember when it comes to divisibility by 6. What is it? 2k into 2k plus 1 is always even. 3 multiplied by this pair is always going to be divisible by 6. That is one thing you would want to remember. That's it for this particular divisibility PMI. Next time we meet, we're going to do inequalities. I'll show you. There. Second part, inequalities is what we're going to do. Let's see. Bye for now.